Hello and welcome back to Web Demo. This is the second part of a two-part demo on statistical design in ADS. I'm assuming here that you have already seen part 1. As discussed in part 1, this is our statistical design process. In this part of the demo, I will use other statistical tools such as sensitivity analysis and design of experiments to help me troubleshoot my design and make it robust prior going into manufacturing. Let me first demo the sensitivity analysis tool. In ADS, we select the sensitivity analysis tool and push the simulate button. Notice that it took 5.5 seconds to perform the sensitivity analysis on 16 variables. Let us now look at the output results and analyze it. This is a plot of S2 sensitivity versus all the 16 selected design variables. Notice that the sensitivity analysis tool shows clearly that capacitor C1 in the output matching network is a very sensitive component. Next, let me demo the design of experiments tool in ADS. In my experiment, I defined 3 variables, each of which represents the variability on its corresponding matching network: input, interstage, and output matching networks. I vary these 3 elements with all possible combinations, and this requires 8 simulation runs. This is a sample output results from ADS on the nominal output and the 8 experiments output results on the spec gain dBs21. From these results, we can extract a lot of useful information. For example, these are Pareto charts with main effects and interaction taken from the output simulated results. Let us look at the S22 spec. This Pareto chart is telling me that 75% of the variability in S22 is due to the output matching network. But the question to ask now, this 75% accounts for how many dB of variability? Does it account for half a dB variation, or does it account for 10 dB of variation, or whatever? Let's find out. The main effect and interaction plot here gives us the answer. What is shown in red is the variability of S22 due to the output matching network, and it is 3.2 dB. This is high and could account for the low yield that we got when we did the yield analysis. All of the statistical tools so far have pointed out that the output matching network is highly sensitive to S22. But this is a mimic. We are unable to control any individual component, like capacitor C1 in the output matching network. Therefore, we have to think of another way. We have to redesign and create a new matching network that is less sensitive and with smaller variation than the one we have right now. Okay, here's our new output matching network redesigned. It has 2 series capacitors, as you can see. This is the amplifier output results with the new redesigned output matching network. Next, the final step is to use the yield optimization tool to center all the design elements in order to achieve the maximum possible yield. Okay, after having fixed the design by redesigning the output matching network, and after having used the yield optimization tool to center the design, we see our final yield now is 97.4%, with most of the Monte Carlo yield runs lie in the pass region. Only few lie in the fail region due to some bad or weak fits that we have. To recap, let me compare the yield for S22 before and after. Initially, we can see that most of the Monte Carlo yield runs lie in the fail region, resulted in a low yield. But after we fixed the design and design centered it, we can see that we have most of the runs lie in the pass region, And also notice the variability. It is narrow variability after we fix the design compared to a much broader variability before. Okay, these statistical tools that we have discussed have helped us find the problem in our initial design, fix it, and raise the yield from an initial 7.2% up to 97.4% before going into manufacturing. Notice here, with the new design, the final design, if we run yield sensitivity histogram on any of the components in the design, we see that it has no variability, no sensitivity, and the yield is very close to 100%. This concludes my web demo. Thank you for listening.